So let's get started. Good morning. So a bunch of announcements just to start things off. Let's see. First, so I don't forget, you may have heard there's a good chance it's going to snow tonight. COA supposedly has a new system for proclaiming snow days. Well, I should change that. We have a new system that has been untested. So have students gotten emails about like how to sign up for the emergency notification system?
Yeah.
Okay.
No, my question is, what if you don't have a phone? Then you don't know there's a snow day?
I think they automatically email you, and you can sign up for a text message.
Oh,
I think so. Yeah.
oh,
Yeah.
I, of course, did not sign up for a text message.
Yeah. So I doubt they're going to, it doesn't look like it'll be too bad. I doubt there'll be a snow day tomorrow. But anyway, this could be a test of the COA emergency system. That in and of itself is a reason for excitement.
Do you want it to be a snow day?
Not really, because it just pushes sort of everything back. However, if many of you live on campus, but some of you drive from the high school, and I live near the high school as well, and there's those fun hills. So if you think it's not safe, I mean, just call a snow day on your own. The classes are going to be videoed, unless I think it's not safe, in which case there won't be any class to be videoed. So anyway, use your judgment, particularly if you're driving away, particularly you guys if you're coming in from the high school. It does look like it's not going to be a ton of snow, but it could be kind of gross because there could be some rain over the night. So sometimes it's not how much snow it is, but it's more like the quality or lack thereof. I think this is going to be low quality snow, in the sense of like bad and slippery. Anyway, we'll see, but don't worry at all about missing class if you think it's unsafe. And if there is a snow day and I still have power, which I usually do, I'll send an email out to the class just so you guys know to not even try. But my guess is that class won't be canceled. But we'll see. And if in the unlikely event MDI has a snow day but we don't, then don't worry about it. Just stay at home. Yeah.
Is it meals on snow days?
Yes. Sometimes it can be like if we lose power, it can be a little bit not quite as haute cuisine as usual. Some might be sandwiches, but yeah, they'll feed you. All right, so those are the fun snow things. So today we'll start talking about vectors. More about that in a second. Human Ecology Forum today, 410. The group that went to Paris will be giving a presentation. I forgot to write it down. I'll have homework help. What did I say? Like 5:30 to 6-ish. So I'll just stop by the dining hall and see who's around. Wednesday, which is tomorrow, we'll do 13.3, maybe even start 14.1. Homework help 5 to 6. Thursday, Nancy sent an email out about this. So she wants to stage a reading of Ta-Nehisi Coates's book, Between the World and Me, which is an astounding book. He's an incredible writer. And so by reading, meaning a group reading, sort of go around in a circle, everybody reads a couple pages. I don't think I can make it for the entire thing, but I'm going to try to go for at least part of it. I would recommend stopping by if you could. I don't know if, because I think she sent it out to community email if that even registered for a lot of folks. But I would definitely recommend that. Homework help. Friday, I'll have homework help a little bit right after my chaos class down in the ES classroom, which is the large classroom on the right in the building that looks like a castle. And I'll need to leave probably right at 3 to head up to Bangor. Ian.
So given the time state has homework up, what would be best for folks? Last week I did mostly evenings in the parking lot. Would evenings continue to be good for you? Yeah. Okay, so I'll send out an email.
Okay.
I'll send an
email. Yeah, send an email. Yeah.
Class.
Perfect. Let's see. Oh, sorry about the mix-up with the due date for the online homework. I think it sort of like defaults. Like when I set up an assignment in the system, some default happens, and I didn't really pay attention to that. And so then a lot of you printed it out with the default, which was like tomorrow. And then I said, oops, I didn't mean that, and changed it to Friday, but you had already printed it out. So anyway, so a lot of people were confused about that. Obviously not your fault, not the end of the world. They haven't even looked this morning to see where people are with the online homework. I'm going to try to get through grading the next day or two. We'll see. If we have a snow day, I'll definitely get through it. The homework for this week, again, is another chunk of web work problems. I think even though there are more problems, they'll probably be a little bit quicker. But I don't really know. I'm not always good at judging how long textbooks problems will take people. I'm probably even worse at the web work problems. And as I said in the email, but it's worth repeating again, what I've done is most of the web work problems are the sort of like quick little, are you adding vectors correctly type of things. And the ones you're handing in on pieces of paper are sort of the harder or more synthetic ones. So I would recommend probably doing the web work ones first. Those are like the sort of short, quick exercises to kind of get some momentum. I mean, you can do them whatever order you want, but that's sort of how I'm conceptualizing these things. The things that are worth writing up are the more interesting problems. Just checking, are you taking derivatives right, is probably maybe a little better done with a machine. OK. Maybe we could do names once more, just to make sure we have it, and it also just gives you a break from listening to me, because then once we're done with that, I'm going to talk about vectors for a while, so it'll be a nice little change of pace. So category, we did animal last time, right? We've done plants and animals.
We have not done fungus yet.
We've not done fungus. We've not done minerals.
We could do
Rocks. I think there are going to be a lot of blank stares from everybody except for Alba. Any other suggestions? Elements, somewhere. I kind of like somewhere you want to visit. Or you could also do elements also if you have strong opinions on that. Teresa, you want to lead us off?
My name is Teresa, and it's either Antarctica or New Orleans.
Yes.
I'm Megan, and I like to go to Canada. My name is Aura, and I think I'd like to go to Buffalo.
I'm Ian, and right now I think Tasmania is on my list.
Go ahead. Sure.
I'm Marielle. I'd like to go to Japan. I'm Heather. I'd like to go to Germany.
I'm Alva, and I'd like to live in Indonesia.
Margarita, and I want to go back to Greece.
Portia. I'd like to go to Greenland. I'm Kenny Primrose. I'd like to go to Hydra, Greece.
To where, sorry?
Hydra, Greece.
Yep.
I'm Aspen. I'd love to go to Mexico.
I'm Jeremiah. I'd love to go to the Himalayas.
And Sydney, I'd love to go to Ireland.
I'm Katie. This is hard. I want to go to a lot of places. Maybe Iceland.
Well, I'd like to go to Brazil.
I'm Jack. I'd like to go to Afghanistan.
I'm Nadia. I would love to go to Pakistan.
Okay.
I'm Dylan. I'd like to go to the Caribbean.
I'm Shinao. I'd like to go to Italy.
My name's Christoph, and I'd like to go to Korea.
My name's Will, and I'd like to go to New Zealand.
My name's Tarzan. I'd like to go to Vietnam.
And I'm Kevin. I'd like to go to China.
Yes. I'm Dave, and I'd like to go to India, among many other places.
People who love cacti said a place there are lots of rivers with cacti.
You remembered who said cacti. I took notes and I didn't remember. People are complicated bundles of contradictions. All right, so thanks for helping me out with that. So vectors. We've seen in chapter 12, that was about multidimensional functions. And we're talking about how they change, rates of change, right? That's what calculus is about. And we've realized really from day one that rates of change depend on which way it's, the direction you're moving. If you think about like on a hill, there's some directions where altitude isn't changing at all, some directions where it's positive, some directions where it's negative, even at a single point. So we're going to have to talk about things with direction, and that leads us naturally to vectors. So chapter 13 is about just building a toolbox so we can work with vectors because we're going to need them a lot in the rest of the course. So there's not really any calculus in these three sections, but it's just building tools that we're going to use a lot once we get into chapter 14 when we're going to start taking derivatives. How many folks have seen vectors before in some form? OK, so that's almost everybody, maybe everybody. So I'm going to kind of say a handful of things about vectors, and then, as usual, just some exercises to start working on. And we'll see where they lead. It's probably nothing too deep. 13.1 and 2 we'll definitely get through today. 13.3, which is about the dot product, I'm hoping to kind of start that today and then do more with that on Wednesday. But we'll just see how it goes. OK, so vectors. Vectors are mathematical quantities that have a direction as well as a magnitude. Right, so something like your mass, 50 kilograms, that's a scalar, which is not a vector, it's just a single number. But something like a velocity, 10 miles an hour at due north, that has a magnitude, how fast you're going, 10 miles an hour, and then a direction associated with it. So vectors, so here might be a vector. And it has a magnitude of 100. This could be 100 meters. It could be a displacement vector. It could be velocity. It could be an electric field. Who knows? And it has some direction, maybe 37 degrees. So let's see. So let's cleverly call this vector v. And so vectors are usually they're a different type of quantity than a scalar. There's more information packed into this symbol than a simple number. It's a magnitude and a direction together. And so they're usually denoted like this, v with some sort of a hat or an arrow on top. When working with vectors algebraically, it's often useful to break this down into components to say that this motion turns out to be the same as that. And normally you would need to do trigonometry to figure that out. But 37 degrees-ish is about what a 3, 4, 5 right triangle is. Useful little thing to know. So if we think in terms of north and east, going 100 meters at 37 degrees in this direction is the same thing as going 60 meters east and 40 meters north. Describes the same displacement. All right. So let's talk about different ways of writing this vector when you break it into components. So let's say x, y, 60. Sometimes you might write it this way. It goes 60 in the horizontal direction and then 40 in the vertical direction. I believe that web work is going to, there are going to be a few problems where you're going to have to enter in vectors. Web work wants angular brackets, not curly bracket, not smooth brackets. I think they sort of tell you that. Like there's a little box you can click on, how to enter vectors. You click on it and a JavaScript thing pops up and it says, do it this way. Anyway. So the directions are often denoted I, J, and then K. So this would be 60 in the I direction, 40 in the J direction. Or you could even translate it right in the X direction and the Y direction. So there are lots of different ways of writing these vectors. I'm hoping at least one of them is familiar. I think our book pretty exclusively uses I, J, and K. I'm a big fan of X, Y, and Z. Sometimes also these little vectors, which are called unit vectors, get hats instead of arrows, a different type of hat, to indicate that this is just a unit vector. It has unit length. I might write this. And there are probably even some ways that that I haven't written down. The point, there are a lot of different ways of keeping track of these things, but the bottom line is vector is a motion. It's a certain amount in one direction, a certain amount in another direction, and you just need to keep those directions separate and remember which is which. This, I think, is more common in physics. This is a little bit more common in math. It's all good. OK. We're good so far? I haven't really said much, so I don't know how it could be going bad yet, but we'll see. All right. So let me mention a few other things about vectors. And then I'll let you discover a few more things about vectors. So if you have a magnitude and a direction, you can break it into components using trigonometry. And sometimes we want to go in the other direction. We have components, or we just want to refer specifically to the magnitude of a vector. So if we want the magnitude only, which you can think of as the length, we just want to know how fast you're going. I don't care what the direction is. That is written in our book like this. It is also sometimes written like this. Physicists are fond of just doing that. Some folks are taking physics now, or have taken physics recently. So maybe, I don't know what, anyway, how you did just the magnitude of a vector. This is kind of bad because it's so easy to mistake that for this, but still physicists do it. Sometimes if you're feeling like really wanting to be explicit, you could write out magnitude. Our book uses this, I think, pretty much exclusively. But I'm mentioning this because depending on the physics classes you've taken or math classes you've taken before, you've probably seen a bunch of these. And we can get the magnitude just by using our friend the Pythagorean theorem. All right, let me mention one more thing, and then we'll just start adding and subtracting vectors, and we'll see what questions arise. It'll often be the case that someone will hand you a vector, and you'll need to figure out a unit vector in the same direction as that vector. It shouldn't be obvious that's often going to be the case. But it will turn out, you'll be perhaps surprised to note in Chapter 14 how frequently you need to find unit vectors. Hence, we will talk about unit vectors now without motivation. So if somebody hands you a vector like this, says this is a nice vector, how would you turn that into a unit vector? Well, you divide it by its own length. So and by unit vector, I mean it just has a length 1. Questions at this point? Again, I haven't really done anything. I've just like asserted some definitions. All right, so let's just start adding and subtracting vectors. So let's just start with these, see how they go, see what we discover, and we'll take it from there. All right, let me rip your attention away, or gently take your attention away for just a moment from the exercises to say a few things about vectors. So vectors are just arrows. And so when you're trying to remember how vectors work, just ask yourself, what would arrows do? Because that's what vectors are. So that's just kind of what always, like when you're confused about vectors, take a step back. Oh, they're just arrows. How do arrows behave? All right. So here, these are the vectors. You just read them off of the grid. Being careful of minus signs. It's easy to lose minus signs here. Vectors B and C are the same. So a vector, again, it's just an arrow. It's not an arrow that's rooted in space. Arrows have no sense of place. So this just says, like the vector I had before says go 100 feet in this direction. It doesn't tell you where to start. So it's just a displacement in a direction, or a speed in a direction. OK, so then I want to take this vector and turn it into a unit vector. I divide it by its own length. So if you have an a and you divide it by one a length, then you have something that has just length 1. So that's what I did here. So these are all from Pythagorean theorems. This one was a 3, 4, 5. C is the same as B. And I guess I just didn't feel like doing E. What is that going to be? 1 over 2 root 2? Or maybe I got bored. Is that right? And you can maybe see sort of how we're going to want unit vectors. So we might want to know, how is a function changing in the x direction? And we'll get an answer, and you'll interpret that. Well, that's the change in altitude if you move 1 unit in the x direction. And then you might say, well, how is a function changing in the y direction? And you'll get the y derivative. And that would be how much the function is changing if you take 1 unit step in the y direction. But then you might say, I want to liberate myself from the xy plane. What if I'm going in a diagonal direction? How you can come up with that derivative as well. And you would interpret that as the change in altitude if you took 1 unit step in that other direction. So we're going to need to figure out how to write down unit steps in other directions. That's where this is headed. OK. I'm guessing we're OK up to here. People seem like that was pretty smooth. OK. All right, so now adding and subtracting and scalar multiplying vectors. So how do you add vectors? Well, how do you add arrows or displacements? Well, it's like one arrow. You do this displacement, and then you do the next displacement. So if you go this distance and then that distance, it's the same as going this distance. So you would add the x parts of your journey, and then you would add the y parts of your journey, one of which is negative or backwards, and you would get your total journey, which turns out to be this. So there are a lot of different ways of writing this, and our book seems to like doing it this way. That's why I wanted to sort of check the textbook. So a plus b, here's vector a, 2i, 6j, and then you add the i parts separately and the j part separately, and you get the i part and the j part. That totally works. I kind of like this way sometimes because basically once you have something into components, 2 or 3 or n components, you've got like 2 separate equations. And this, if you just sort of stack them right on top of each other, you're much less likely to maybe mix up an I and a j, particularly since I and j, if you're going quickly or you're tired, i's and j's turn into each other very easily in handwriting. Maybe that's just me. Anyway, our book doesn't do this, but you should just do whatever you feel happiest about. And again, if you're taking physics or have taken physics, you may have already kind of gotten a style. Just go for it. So all of these different ways of writing vectors, they're all just arbitrary conventions. So they're all equally right. But some are more common than others. I would say, but actually, well, they're all quite common and more or less interchangeable. The one exception is this funny angular bracket thing, which is more a quirk of web work. It's pretty unusual to write vectors this way. These actually would mean, often to me, would mean something different. But if you define them to mean vectors, that's fine. So this is more of a web work thing, and I think it's because web work wants to interpret, doesn't know contextually that you're telling it about vectors. So if you did it like this, it would interpret this as parentheses, not knowing they were special vector indicators. OK, so that's adding vectors. Vectors add tip to tail. So subtracting vectors, I always have a little bit of a hard time picturing this. And so the way I always think of this is, all right, so here's the vector c. The vector minus c is the backwards vector c. That means you flip it around, because c plus minus c better equal 0. So like minus c undoes c. So then I can draw this picture here. Well, what's a minus c? Well, that's a plus minus c. And I know what minus c is. It's backward c. So I do a, and then I do backward c. And then this vector in yellow would be a minus c. Yeah?
I think you missed the minus sign. On 3. Just because it doesn't make sense that it can be negative 2i plus 3j, because, like...
For the C component, the J component is
Yeah.
minus.
Then that makes us 9? OK. That does look a little more like that. OK, thanks. So I was going to say, it's relatively easy just to sort of not think about the pictures and do the algebra, and as long as you remember the minus signs. So I think one of the challenges with vectors is, once you sort of see how the mechanics work, it's a crank you can turn, break into components, do the things you need to do. But there are times when you want to come up for air and ask yourself, as you guys just did, wait, do these numbers, might as well change that one too, right? Do these numbers make sense with this sort of picture? OK, so lastly, there was I think it was 2b. Was that the one? 2b, OK. So what's 2b? Well, that's b plus b. Right, so that just takes the vector and stretches it. It doubles it. You're doing b twice. If it was half b, you'd only do half of a b. So 2b would be 8i minus 6j. So this is called scalar multiplication. And because 2 is a scalar, it's just a number. And it doesn't change the direction. It just stretches or compresses the vector. All right. Questions on any of these? So let's now do problems 3 and 4 on the back. 3 is another just quick little calculation. And 4 will be a word problem that will require some cogitation. And I think I'd like to skip 5. So let's do 3 and 4 and see how it goes. All right. So For this one, as with a lot of stuff with the vectors, and particularly these more physicsy problems, a good drawing is a key to success, I think. I often, because I sometimes get west and east mixed up, I'll label, like just draw one of these to remind myself. And I also, like east of north, I have to sort of talk myself through that. So you start north, and then you're going east of north. So again, like having a little compass thing on your paper can be helpful. So the picture here is there's a wind coming down this way. And if the plane goes at this this direction, it ends up moving due east. So what must be happening is that the up and down on this graph, the up and down component of the plane speed exactly cancels the wind speed out. So another way of thinking about it is we're sitting on the ground watching this happen overhead, and we see two motions added together, a wind motion and a plane motion, and that those motions together, we end up observing the plane traveling due east. So then once we have it in this picture, it becomes basically a trigonometry problem. Cosine of 60, it can be helpful, again, to write down adjacent over hypotenuse. It's easy if you're going a little too quickly to get things twisted around. So there's a right angle, adjacent hypotenuse. And if I plug it in and then remember it's a 3, 4, 5 triangle, or that cosine of 60 is a half, we end up with 160. So for these problems, I find the biggest challenge is sort of getting the picture right. Once you sort of get the picture pictured, then the trig usually sorts itself out. Questions on this one? All right. So what I'd like to do now is say a little bit about the dot product, and maybe have you do just a couple of quick dot product-y exercises, and then I'll do a bunch more with the dot product tomorrow. All right. So far, we know how to add and subtract vectors and do scalar multiplication, but scalar multiplication is really just addition, because like 2b is b plus b. And so there's another really key operation on vectors called the dot product. And dot products in different guises come up again and again and again in math and in physics. So we'll spend a bunch of time on them. The cross product, which is 13.4, we're going to skip until we need it at the very end of the course. So cross products don't come up that often, whereas dot products are just sort of an everyday fact of life in math and life. So dot products turn out to be surprisingly important. So a dot product, it's a way of multiplying two vectors together. So the question is, like, well, what might be a logical way to do that? Well, it's like numbers, we just multiply them. But vectors also have this direction. So we want to do something that's multiplicative, but at the same time doesn't ignore the direction. And so that leads us to this dot product idea. So here's a picture. We have two vectors, v1 and v2, and we multiply them together in this special way as follows. So I guess let me write the definition, and then I want to give a geometric interpretation of it. And then I'll write a formula in components. So v1 dotted into v2 is v1 so magnitude of v1 times the magnitude of v2 times the cosine of the angle between the two vectors. So you need to line up the two vectors so that their tails are adjacent, and then this angle would be theta. And so what this has the effect of doing is it multiplies v2 by the part of v1 that's in the direction of v2. Or you could think of it, it multiplies v1 by the part of v2 that's in the direction of v1. Let me draw a picture to justify that, because I know those words, are true, but not necessarily helpful. So let's see, what do? I'll draw a bigger version of this picture. v2, theta, there's v1. And I want to know maybe what's that distance. So, this is trigonometry again. All right, so cos is adjacent over hypotenuse. That's the ka in SOHCAHTOA. Adjacent over E1. So equals the part of v1 that is in the v2 direction. Or you could even think of it as the v2 component of v1. So here's a picture. We're multiplying two vectors together, but direction matters. And so v2 is saying, all right, I'm going to multiply. I get multiplied to me this v1 part, but the only part that really helps me or contributes to what I'm trying to do is the part of v1 that's working with me. So v1 is partly in the direction of v2, but not entirely. What part is in the direction of v2? It's this component, which is given by the cosine. So it's a way of multiplying vectors together that takes into account their directionality in a certain sense. Yeah?
So is the component of v1 that's not in v2 then just kind of to the side, like not part of the equation?
Exactly. It's ignored. Yeah. So if I were to take another vector, v3, and another vector, v4, those would all have the same dot product. Because v2 is saying, I don't really care what you're doing in the other direction. That means nothing to me. It neither hurts nor hinders me. It's just completely different. I just want to know how much of you are with me, and these all have the same amount of them with it. So another even more geometric way to think about this is that it's the projection of v1 onto v2. And so the picture is it's so like if I had a up here where I can't quite reach, if I had a bright light pointing down, it would be the shadow that these vectors would cast. And so all of these vectors cast the same shadow on v2. So let's see. So this is one way of thinking about the dot product, and it's one way of calculating the dot product. Right? I mean, this is a formula you can use, very, very useful formula. There's another formula for the dot product that I want to mention, which works with components. So if you have two vectors in components, so the idea here is you multiply the x components and you multiply the y components. And note that the dot product, the answer to the dot product is just a number. It's not a vector anymore. So this is sometimes called a scalar product. It's a way of combining two vectors and getting a scalar out that tells you has to do with the magnitudes of the two vectors and the extent to which they point in the same direction.
You actually use AC/BD.
Yes. Sorry. Okay. Plus BD. Yep. All right. There's lots more to say about the dot product, but let's do 6. Let's see if we can get through 6, 7, 8. Well, let's start with 6 and see how far we get. All right, so let me say just a few things about this problem in the 5 minutes we have left. We'll do lots more with the dot product next time. So there are lots of fun, useful things that one can do with a dot product. And one of them is it lets one think about, calculate angles in an interesting way. And in fact, I almost think of it as defining angles, and I'll say what I mean by that in a second. So all right, A and B, we do the dot product with components. Just multiply, multiply, add, boom. But we have another formula for the dot product that's equivalent. Magnitude A, magnitude B, cosine theta. We can figure out A and B. And then we know everything in an equation except for cosine theta. Awesome. We solve for cosine theta, invert that, and we end up with 101 degrees or some amount of radians, pi over 2 plus a tiny bit more. So, and if you draw a picture, you can say, oh yeah, this looks like 101 looks like it's about right. So here's one of the sort of fun things about this approach. So imagine instead of working in 2 dimensions, we were working in 5 dimensions. So the vectors here obviously wouldn't be spatial. These could be like a 5-dimensional price vector or something in economics, right? And maybe you have 2 different price vectors. And you want to know what's the angle between these 2-dimensional price vectors in 5-dimensional space. Because it's like, are they kind of pointing in the same direction or not? I'm like, well, OK, so good luck drawing that. However, we know how to do that, right? If we had 5 components, we'd just multiply 5 components together and add them. We'd do a 5-dimensional Pythagorean theorem. It extends naturally. And then we just get a number. We take the inverse cosine of that. And we get the angle between vectors in an arbitrary dimensional space. So anyway, I just wanted to end this way because we've done absolutely nothing deep all day until this particular moment. So anyway, if it just seemed like, OK, we're just kind of like learning some tools, that's exactly right. This was pretty basic learning of some tools. We'll use these dot product tools to think about other ways of thinking about planes, which are going to be really important. So we'll use dot products in some more interesting ways, practice dot products some more, and then we'll probably start with derivatives next time as well. So a class is coming in here in a couple minutes. I'll be up in the dining hall for 5 or 10 minutes. And I'll see you tomorrow. Be safe in the snow.